Okay. So today I want to finish off an example that from the last chapter and start the next chapter, which is essentially how to compute correlation functions. So this is really the meat of this course and pretty much everything that we've been building up to. We've defined what the Fock space is, talked about what the conformal symmetries are in the theory, and now we're going to take a conformal field theory and we're going to impose conformal symmetries, and we're going to see how the conformal symmetries restrict the correlation functions. So I'm going to tell you today what correlation functions are, just the general structure of them. We're going to talk mostly about the operator formalism rather than the path integral formalism for correlation functions from this section. But that's largely because we're going to see that essentially the symmetries of the theory are so constraining that they're going to give us essentially the 1-point correlators, the 2-point correlators, almost the 3-point correlators, and certainly the form of the 4-point correlation functions. Right, so they're going to completely fix these correlation functions. It's a huge deal, right? So the correlators are the observables in the theory. Once you know what these correlators are, you know everything that there is to know about the theory. We're going to calculate them for primaries, for primary scalars, and then I'm going to show you, once you know how to calculate the correlation functions for the scalar primaries, calculating them for all the other operators in the same multiplet is roughly trivial. It is done by taking derivatives, so calculating for secondary operators, etc. And then we'll do a couple more operators that go beyond scalars. So we'll calculate correlation functions for conserved currents and for the energy momentum tensor. Right. So these are all the observables in the theory. And I'll show you just how strongly constraining conformal symmetry is on the theory. But today I'm just going to tell you what these correlation functions are, what they generally look like, and we'll build on it from there. A big chunk of what we're going to be talking about will rely on the fact that we're calculating correlation functions in theories in which the symmetry of the theory is not spontaneously broken. As you may know from your particle physics course, or maybe your conformal, or maybe your quantum field theory course, a theory exhibits spontaneous symmetry breaking when its ground state doesn't exhibit the same symmetry as the theory on the whole. So for theories that have spontaneous symmetry breaking, you have to do something else, right? So you've got to be a little bit more, it's a little bit more nuanced than what we're going to do. So we're going to focus on theories that do not exhibit spontaneous symmetry breaking, and this will feature as a specific constraint of the states in the theory. Right? So we're going to use it explicitly in our derivation of the Ward identities. Now, we've derived the Ward identities already previously using the path integral method. Just, you know, for some change, I'm going to derive it again, both in the infinitesimal form as well as in the finite form, using the operator formulas. Okay, so we'll do that today, and that will set the stage for computing the correlation function. So next time, I will do probably the 1- and 2-point correlation functions. That's really where the heavy lifting takes place. And then the 3-point functions follow in the same way. And the 4-point functions, I'm just going to write down the answer because it's a lot of the same thing. And then I want to, it depends on how much time we have. We've still got 7 lectures. I would like to cycle back to, if we get through, you know, conformal bootstrap and stuff, then I want to revisit this idea of computing the 4-point correlation functions, because the 4-point correlation functions are really the things that tell us about the interactions of the theory, right? So in particular, if you're doing what is currently very fashionable, quantum chaos, for example, then you want to calculate 4-point functions. You want to calculate a specific type of 4-point functions, but they give you a lot of information about the theory. In particular, the 4-point function is related to something called the square of the double commutator. It's something called the square of the commutator, and the square of the commutator is the quantum equivalent of the Lyapunov exponent. So being able to calculate that in a theory is hell of important. But as we're going to see, even in a conformal field theory where you've got a substantial symmetry to constrain your correlation functions, it doesn't completely constrain the 4-point function, right? So I would like to cycle back to the computation of the 4-point function and show you how we can use a nifty trick called the shadow formalism to kind of double your theory and write down the 4-point function in terms of 2-point functions from your original theory and your shadow theory to build a 4-point function. And then it translates this story of computing the 4-point function into integral representations of the hypergeometric equation. So there's a lot of really beautiful math in this story as well. But for the moment, I want to start with an example. And the example I want to do is to try and apply the ideas that we were talking about for the last couple of lectures to a rather simple theory. And this is a free scalar field theory in 3+1 dimensions. So consider the free scalar field in D equals 3+1. So this thing is defined by an action. Action is simply a functional of phi is integral d for x a half d mu phi d mu phi. It's a free theory. And in addition, I'm going to assume that this field phi is massless. Okay, I just want to make a point here. I'm not, we're not doing anything that's particularly physical. So consider this theory. What I would like to show you is the following fact. When a theory starts to develop negative norm states, we will start to see the appearance of null states. These are states with zero norm in the spectrum of states of the theory. What I want to show you is that if I take this to be a primary field, so I've got a scalar primary on my hands, that the level 2 descendant of this field has zero norm. So it's a null state of the theory. Okay. But before I get there, we should do some dimensional analysis. To determine the scaling dimension of this guy. Okay. So we'll start by making the point that we're working in natural units. So in natural units, I'll use the fact that c equals h bar equals 1, the speed of light, and h bar is both set to 1. What this means is that they're dimensionless numbers. They're just numbers, okay? And the way I denote that is to say that the dimension of c, the dimension of h bar, about 0, okay? That's how I'm going to denote the fact that these are just numbers. But we know that the dimension of the speed of light is the speed, right? So the dimension of c is the dimension of length times the dimension of time to the -1, right? It's a length per unit time, speed. Similarly, well, what this means is that the dimensions of length must equal to the dimensions of time so that their dimensions cancel out. Okay, and they give you something that's dimension 0. Similarly, by looking at h bar, we learn that the dimensions of mass must be minus the dimension of time. Okay. That's because energy is h bar times the frequency, right? And energy is mc squared, and c is 1. So energy and mass have the same dimension. Therefore, the dimension of mass must be minus the dimension of time. So we're going to measure everything in mass dimensions. And we're going to count this guy. We'll say that this has mass dimension. Mass has mass dimension +1. So if mass has dimension +1, then time has dimension -1. Length has the same dimension as time, so length has dimension -1. Okay? So that's how counting is going to work. And if that's the case, then you'll recall that the action enters the path integral as an exponential of the action divided by h bar. But h bar is dimensionless, which means that the action has to be dimensionless because it's the argument of an exponential. Okay? So the action is dimensionless. So S has dimension 0. And S is the integral of this guy here. Derivatives have dimensions of inverse length. If length has dimension 1, so this is 1, which means that length must have dimension -1. So if length has dimension 1, inverse length has dimension -1. So there's -1 from here, -1 from here. There's 4 lengths coming from here. Overall, this has to be dimensionless, which means that phi, the dimension of phi, the engineering dimension of phi, has got to be +1. This is a dimension 1 operator. In fact, this dimension is its conformal dimension. It's a scaling dimension as well. Okay, so we're looking at a scaling dimension 1 operator in the theory. This field phi, or operator phi, corresponds to a particular state via the state operator map. Let's label it by phi as well. So the operator phi of x corresponds to the state phi in the Hilbert space of the theory. And the representation of the conformal group on this Fock space is defined by the action of the generators of the conformal group on this state phi. So the action of the generators of the conformal group on which the generators act as follows. D phi is just I minus I times phi. And this is because the dimension of phi is 1. Generator of Lorentz transformations on phi is 0. That's because we're talking about a scalar, so it doesn't carry any Lorentz indices. And k mu phi also vanishes. And that's because phi is a prime ring. Okay. And as usual, descendants of phi are generated by acting on phi with p mu, right, with derivatives. So my claim is that when a theory is about to develop a negative norm, we will find some states in the multiplet of phi that are null states, right? It means they have zero norm. And in this case, let's show that this delta equals 1 is a bound for the scalar operator by showing that the descendant state is the level 2 state associated to phi. So the claim is the level 2 descendant state, let's label it like this, by its level number, which I get by two actions of p on phi, is null. So let's check this. We'll check it by computing the inner product of 2 with itself, using the fact that when I conjugate this guy, I produce k's, right? So this is just phi k mu, say k mu, p mu, p mu, phi. So let's calculate this thing. In particular, I want to show you that that k mu p mu is 0, acting on phi. So let's consider the following state. K mu p mu on phi. I know that phi is a primary, so if I take these two and consider them one operator and k mu is one operator, then I can replace this thing on the left-hand side by the commutator of the two, right? Because k mu acting on phi is 0. So this is just k mu, p mu acting on phi. And then I know that the commutator obeys the product rule, so it's Leibniz. So this is p mu k mu p mu on phi plus k mu p mu p mu, and then it doesn't really matter whether I have this up or down because we're in flat space after all, like such. Okay. So this comes from the fact that phi is primary. And this comes from the fact that the commutator satisfies product rule. In other words, it's a derivation. But I also know that this guy here, K mu commutator K nu commutator P mu, this commutator is just 2I times eta mu nu times the dilatation operator plus m mu nu. Right? You would recall that the last time I wrote this down, there was a minus sign here, but I've got a nu here and a mu here, so I would write that with a minus sign nu mu, but this is an antisymmetric object, and therefore the plus. Now we understand where all the signs are coming from. And then replace everywhere I see this commutator in this expression with 2I times eta mu nu d plus m mu nu. So this is, oh, why have I gone to the other report? Sorry. So this is equal to 2I eta mu nu d plus m mu nu. That's this guy, P mu on phi plus 2I P mu times eta mu nu d plus m mu nu acting on phi. So now we use in here the following. The first expression we need is that I m mu nu p nu. That's right. I m mu nu p mu is I p mu m mu nu plus delta mu nu p nu. What's free here? Mu. So p mu minus 4 p nu. This delta replaces this mu with a nu. So there's 1 from there, minus 4 from there is 3. So this is just I p m mu nu minus 3 p nu. So if I commute the p's and the m's, I'll pick up this term that goes like minus 3, right? And this comes from the fact that we're working in 3 + 1 dimensions. And then I know also that I d acting on phi is phi. I d p mu acting on phi is just 2 p mu acting on phi. That's because phi has dimension 1. P increases its scaling dimension by 1, so it's the eigenvalue of ID with it's the eigenstate of ID with eigenvalue 2, right? So it has scaling dimension 2. And we're still talking about scalars, so mu nu on phi vanishes. And when you substitute all of that into this relation here, which means that it is equal to 4 p nu on phi minus 6 p nu on phi plus 2 p nu on phi. Go through the calculation yourself to convince yourself that this is the case. And 4 plus 2 minus 6 is 0. So indeed, the level 2 descendant is a null state. Okay. This corresponds to a null state in the free scalar. This is not too difficult to understand. The reason why we have such a null state, if you go back to the equations of motion for this theory, the equation of motion for the free scalar in 4 dimensions is nothing but the Laplacian of phi equals 0. So d mu phi equals 0. Well, d mu phi equals 0. Each p mu pulls on a derivative. So p mu is just d mu, and that's equal to 0. Okay. Okay. Good. So that brings to an end the chapter on representation theory of the conformal group. We now know how to organize the Fock space in a conformal field theory. What I want to do now is tell you how this constrains correlation functions. Again, correlators in the theory are the main objects in the conformal field theory, in any quantum theory, in fact, right? They happen to be highly constrained in a conformal field theory. But if I know all the correlation functions, and we've just learnt now that if I know all the correlation functions of primary operators in the theory, then I can construct the correlation functions, or I'm going to show you that you can use that to construct the correlation functions for descendant operators, right? It's still a lot of work, but you can do it. So in principle, you can completely solve a conformal field theory if you know what the correlation functions for primary operators are. Okay, so that's why we talk about them with so much reverence. So what are we, chapter 7? Okay. So a correlation function is basically a function on my theory space. So it takes in some points in space-time and it returns a number. Okay, and this is going to be an important philosophical point to keep in mind as we go forward. So a correlator or correlation function is an object of the form an endpoint correlation function O1 of x1 O2 x2 On xn. And what we'll mean here is that you sandwich the operator O1, x1 to On, xn between some states omega. So this is some general state in the theory, which we will usually take to be the vacuum state in the Hilbert space. So this is some state in the Hilbert space. And for all our purposes, we will take this to be the vacuum. All right. And these guys are some set of, so the OIs of xi is some set of local operators in the theory. So there are a couple of points that we have to make. That will impact the calculations that we want to talk about. So just by way of example, if we think about what such objects might mean, if you take, for example, an Ising spin chain, so this is a chain of spins in 1 or 2 dimensions, that is a model of, for example, a ferromagnet in 2 dimensions, then, you know, a correlation function like this might tell you how spins interact with each other over some distance, right? So I asked about the spin. The O's could correspond to spin operators like the Pauli matrices, and the X's will tell you where on your Ising chain this operator acts. And by asking about a correlation function like this, basically you're asking how knowing what the spin at this point is tells you about the spin at this point, right? The correlation between these fields at different points. Another way to think about this is that these O's are operators in the theory. I take a product of these operators, and then I take a quantum average over those operators, right? And how you choose to take your quantum average is up to you. In the past, I've motivated that you would calculate a path integral in the same way that you would calculate an integral when you want to calculate an average of a quantity in first-year calculus. But we're going to be largely talking about the operator formalism in these lectures, because we can get away with it. Point number 1 is the correlation functions because they're observables must be invariant under the same set of symmetries that the theory is invariant under. Right? So if my theory has some symmetry, the correlation functions must have that same symmetry. We already know that the fields themselves are not invariant under that symmetry. They transform covariantly, right? In other words, there's some change that happens when I make a symmetry transformation on the field. But these guys are observable, so they must be blind to that change. So however they're constructed, right, whatever this thing means, when I make transformations on the fields O1 through to On, this object here had better be invariant. If it's not invariant, then I've done something wrong. So the correlation functions, the correlators in the theory, must have the same symmetry. Must be invariant. In particular, what this means for us is that the correlators in the CFT must be invariant under the full set of conformal transformations. This is important. In fact, enforcing invariance of the correlation functions under the full set of transformations will lead us to a set of constraint equations that all the correlators in the theory must satisfy. These are precisely the Ward identities that we spoke about previously, right? So enforcing this invariance leads to the Ward identities, which again are a set of constraints that all correlation functions must satisfy. So then if you go back to what I said here, if you go back to what I said here, if you go back to what I said there, in order to compute this average on the left-hand side, I need to know the action of these operators on the state that I'm choosing to evaluate the product on. And I said, by and large, we're going to be choosing the vacuum state. So I need to know what the action of the operators and the symmetry generators are on the vacuum. Okay? And we're going to assume that the symmetries of interest, specifically conformal symmetries, are not spontaneously broken. Now, what does spontaneous broken symmetry mean? It means that the vacuum state, the lowest energy state of the theory, does not possess the same symmetry as the theory, as the full theory. So, so what this means is that for any transformation G, say, of my symmetry group, that the vacuum state of the theory is invariant under the action of some representation of G in the Fock space. So if I've got a symmetry group capital G and little g is some element of capital G with representation U of G in the Fock space, then U of G acting on the vacuum is the vacuum. The vacuum is invariant under the action of U of G. And similarly, U dagger acting on the vacuum leaves it invariant. Okay. So we're going to need this just now. So this is all we need to know in order to derive the Watt identities for the theory. So I'm going to derive the Watt identities in both its infinitesimal form and its finite form, because both are going to be useful for what follows. So now let's derive the Watt identities. So the first point to note is that we're going to make some symmetry. So we're going to make some transformation, infinitesimal transformation on the coordinates, and that's going to induce a transformation on the operators. So x mu to x mu tilde, and x mu tilde is going to be x mu plus psi mu, where this guy must satisfy some killing vector equation. If it's a conformal killing vector equation, then we know how to solve it, and we get conformal killing vectors out of it. That's not going to be important for us right now. What is going to be important is that under that infinitesimal transformation, the operator OA, where A is some catch-all for the Lorentz indices. I'll just tell you how the Lorentz indices transform. This guy goes to some O tilde of A, and O tilde of A is U of G, O, A, U dagger of G. And this can be put in infinitesimal form by Taylor expanding, essentially gathering terms OA plus some delta OA, whose form is not really important at this point. But it gives us the basic ingredients that we need. So we're interested in computing the endpoint correlation function given in 1. So vacuum O A1 1 of x1 all the way through to OAN ONX ONAN of xn on the vacuum. These are Lorentz indices. These are labels. These are points in space-time. So what I do is I can use the fact that these U's are unitary and write down the identity everywhere in between here. And then I expand the identity as U dagger of G, U of G, O1 A1 of x1, U dagger of G, U of G, O2 A2 of x2, and so on until U of G O A N O N A N U dagger of G U of G on the vacuum. Okay. So then I use the fact that the symmetry is not spontaneously broken. So the action of U on the vacuum leaves it invariant. So this guy here is just the vacuum. And the action of U dagger on the vacuum leaves it invariant. So this guy here is also just the vacuum. So this is just the vacuum U of G O1 A1 of X1 U dagger of G. And it goes on until I get to this guy, which is U of G O-N A-N U dagger of G on the vacuum. Right? But this object U O A U dagger is just the transformed operator. And that transformed operator is just this. So I can replace all of these guys. So O1 A1 tilde to O-N A-N tilde X1 Xn on the vacuum. And then I expand the vacuum. And then I gather terms, right? And when I do that to lowest order to leading order in the deltas, in other words, anything that goes second order, delta squared and above, I drop because these are infinitesimal transformations. This becomes O1 A1 of X1 all the way through to O-N A-N X N O plus the vacuum, delta O1 A1, O2 A2, all the way through to O-N A-N on the vacuum, plus other terms where for each one of these O's, I replace it with a delta, right? And then I look at the left-hand side and the right-hand side, and I have this plus, I have this on both sides, so they cancel out, which means that this is only true if all of these terms vanish. So this necessarily means then that the sum over I equals 1 to n of the correlator O1 A1 at X1 plus delta OI AI at XI due to ON AN at XN. In other words, I'm just replacing the ith term here in the sum. All of these are summed to 0. And this is the Ward identity. And if you go back and recall what we did previously with the Ward identity, it's exactly the same, except we use the operator formalism to derive it. Okay, this is the infinitesimal form of the Ward identity. We will cover the finite form of the Ward identity on Friday, and I'll use it to constrain correlation functions.